Hello and welcome to our video introducing how we can finally find the reactions of indeterminate beams. And so if we look, we actually have a beam that is fixed at A. It should behave like a cantilevered beam. We have this triangular load W of X that has a magnitude of W at B. But at B, we've added this additional roller. So suddenly we become statically indeterminate. When we look at our free body diagram, we know we have a vertical reaction at A and B. We also, though, have the moment at A, and we have this possibility of a horizontal force also at A, which we can tell by observation goes to zero, but that's using statics. So that's using one of our statics equations. So boom, there it is. We sum forces in the X equal to zero. We get AX. Now we can sum moments at A. And when we do that, we can write an expression for the moment at A, because of course we have to add that in terms of BY and WL. Now you could sum forces in the Y or sum moments at B equal to zero to find your other equation, and I'm going to sum forces at B, and so I get another expression for M sub A. I can't sum forces in the Y because I already sum forces in the X. I've used my three equations. But what turns out here then is we have three unknowns, MA, BY, and AY, but we only have two equations. So what are we going to do? Well, it turns out we have some tools to our advantage that we can try to use to solve this problem that before we were told weren't solvable. So thank you, strength and materials. We're going to use kinematics for our third equation. Kinematics is known as the geometry of the deformation. It's the geometry of movement. In our case, the movement is deformation, and our deformation is the V of X equation, or the equation of the elastic curve. So we're going to need that. And so it'd be good for us to go back to the original beam and see, what does that deformation look like? We know it should look like a diving board sort of deformation if the roller wasn't at B, but with the roller at B, we're going to see that it will curve back up. And so there's our drawing of the deformed shape. So to write our V of X equation, we know what we have to do with integration. So we're going to need to find an M of X expression and integrate that, and of course we can do that in one cut. So let's go ahead and draw our cut shape. And as we draw our cut shape and do our first cut, it's going to be valid from 0 less or equal to x less than or equal to L, because our load is continuous. And our W of X, we can actually rewrite as the magnitude at the top of WX over L, regardless of what X is equal to. And then show our support reactions and our internal members at the cut, our V of X and M of X in the positive direction. Now, if you're not sure how I got that W of X expression, here's a quick video. You can pause on this, but basically just using similar triangles, we know we're W magnitude at the top of the triangle when we have L, and so we're some W of X, and we can solve for that. All right, so coming back to our beam, once we have established what the magnitude is of the top of the triangle, which is our WX over L, then we want to find the resultant, and it's good to put its location. We know in a triangle it's 1/3 of the way from the cut, or 2/3 from A, 2/3 of X, and then of course it's just the magnitude of the triangle, WX over L, times the length X times 1/2. So with that information, we sum moments at the cut, and we can write our M of X equation as MA/AYX minus WX cubed over 6L. And we know our slope is nothing more than the integral of the M of X equation. And it's super important, right? We have both MA and M of X in that summation to zero equation. Plug it into our sigma of X, or I'm sorry, theta of X, so our integral. And when we integrate that, we obviously end up with a constant of integration that comes back out. Now we have a choice here. We could integrate again and go straight to displacement, but if we look back at our deformed shape, we actually can see whenever you have a fixed member, like at A, a fixed case, that means zero rotation. So we know the slope at A has to be 0. So let's just do that boundary condition. So at X equal to 0, theta equals 0, so C1 equals 0. So let's get rid of it and make our life easier. And now we can go ahead and integrate the slope. So let's go ahead and just rewrite the slope expression, but now behind an integral. So just taking the C1 out. And when we integrate that, we're going to end up then with a term that also has our C2 in it, but here's now our expression for v of x. And now we can look at our additional boundary conditions. And in this case, we can see that not only do we have zero displacement at A, so at x equal to 0, the displacement is 0, that's going to lead to C2 0, but because of that roller at B, we also have zero displacement when x equals to L, and this is valid in this equation because our cut is valid from 0 to L. So when we plug that in, we actually get another expression that has this unknown moment in it and this unknown AY in it. And we can call that equation 3. So now we have 3 equations, 3 unknowns, exactly what we needed. And in fact, notice equation 2 and equation 3 have both the same terms, unknown terms in it. So why don't we just plug equation 2 right into equation 3? Whoops, and I just remembered I had forgotten to press enough buttons, so that is definitely AYL cubed. But let's put that equation 2 into equation 3. And as we plug that in, there's our M of A, right? Plugged into that first term. And then we can fill out the rest of the equation. So AYL cubed over 6 plus WL to the 4th over 120. AY is the only unknown in that expression, so we can find that as 9WL over 40. Now just plug that back in, right, to equation 2. And we get that our moment is actually negative 7WL squared over 120. Because it's negative, we want to make sure I'll write it positive, but draw our moment going the opposite direction that we assumed. And then put that into equation 1, and we get our BY. And so now we have our AY, our BY, and our moment at A. So by simply doing our statics equations, recognizing that we didn't have enough information to find our reactions, we actually then just go back to our good old kinematics, write our deflection equation. It's just now, instead of it being all numbers, it has to be carrying unknowns like the moment at A or the reaction at A. We carry that all the way through. But because of that extra support that made us redundant, we get an extra boundary condition. So we can solve our 2 constants of integration and an unknown reaction. All right, take some time, watch this. Thanks for watching.